Welcome to the 5th episode of Online Mathematics for Secondary Schools. In this mathematics lesson, we shall be studying Surds. Surds is a very important topic in secondary schools mathematics. At the end of this episode, you should be able to differentiate rational numbers from irrational numbers. You should also understand the guiding rules of basic Surds operations, and also evaluate expressions involving Surds. And finally, you should be able to apply Surds to solving problems. Your mathematics teacher is Dr. Oluwabukola Daniel. Please have your writing materials so you can take notes as you watch this lesson. I will now be handing you over to your mathematics teacher, Dr. Oluwabukola Daniel. Have a happy viewing.
Today we are looking at mathematics for senior secondary schools, and I'm your tutor, Oluwabukola Daniel. We are looking at Surds today, and at the end of this lesson, I hope you'll be able to get some things out. Some of the objectives of this lessons are: the first thing, I would expect you to be able to differentiate between rational and irrational numbers. You should also be able to explain what Surds are. You should understand the guiding rules of basic Surd operations. You should also be able to evaluate expressions involving Surds. And finally, you should be able to apply Surds to solve triangles involving special trigonometry ratios. So, what are rational and irrational numbers? A rational number is a number that can be expressed as a ratio of two integers with the denominator not equal to 0. So what do I mean by that? So say you have 2 over 3. That's really a rational number because it can be expressed as a ratio of two integers. Why? Just like you would expect, an irrational number is any number that cannot be expressed as a ratio of two integers. That's P over Q. You cannot express an irrational number like that. So an example of this is root 2. If you look at root 2, for instance, you cannot break root 2 down further into two integers and that are rational. So what are Surds really? A Surd is a square root which cannot be reduced to a whole number. So it can also be viewed as a root of rational numbers which cannot be expressed as exact fractions. So an example of this would be root 2 or root 5. If you look at root 2, for instance, you cannot break it down further, just as you would expect. And the same thing goes for root 5. But let's see, what do you think of root 4? Do you think root 4 is a Surd? I would say no, because root 4 can actually be further simplified into 2 times 2, which is 2. So root 4 is not a Surd. But numbers which cannot be broken down further into whole numbers are Surds, just like root 2 and root 5, as we said before. Looking at the general Surd rules, these are actually guiding principles when resolving Surd-related problems. And we'll have 4 basic ones which we'll be considering at this time. So the first one has to do with multiplication. If you have two numbers which are being multiplied, they can really be simplified into this. So if you say, for instance, you have 2 times 3, root of 2 times 3 can be broken down into root 2 times root 3. The same thing goes for division. If you have root of P over Q, it can also be expressed as root of P divided by root of Q. So for instance, following the same trend as we have above, so root of 2 over 3 can be written as root 2 divided by root 3. But with addition, this rule does not generally apply directly with addition. So if you have root of p plus q, you cannot write it as root of p plus root of q. So what do I mean by this? That means if you have 2 plus 3, that's a plus, 2 plus 3, this cannot be written as root of 2 plus root of 3 because root of 2 plus 3 is 5, so you cannot break that down that way. The same thing goes for the subtraction. If you have root of p minus q, it cannot be written as root of p minus root of q. So from this example that we have here, root of 8 minus 3, which is the same thing as 5, cannot be broken down into root 8 minus root 3. So those are the basic guiding principles. Let's look at examples at this particular time using these basic rules. The first thing is root of 12. If you look at root of 12, for instance, using the first rule that we have, this can be broken down into root of, if you have the prime factors of 12, so this is actually root of 4 times 3. So this, in the same vein, using the first rule that we'll have, is the same thing as root 4 times root 3. Remember, root 4 is the same thing as 2. So this actually gives us 2 root 3. Let's look at another example, which is root 12 times root 3. We would also be applying the first rule. But one thing you should take note in the first rule is it is vice versa. It can go in either direction. You can decide to say root 12 times root 3, or say root of the multiplication of this inside all in one bracket. So we'll still be applying the first rule in this particular example. So root of 12 times root of 3, what we'll then do is to expand this and bring them inside one bracket. So we'll have 12 times 3. So this is the same thing as root of 36. And we all know from our multiplication table that root of 36 is the same thing as 6. So just like I said, the rule goes vice versa, like either sides. So we have applied the first rule in solving these two examples that we have. Now, looking at addition and subtraction of swords, knowing fully well that in the 4 basic rules we talked about, they cannot be applied directly to addition and subtraction. So let's see how to go about addition and subtraction of swords. One basic thing to note when carrying out addition and subtraction of swords is that only swords with the same basic form can be added or subtracted. So they must have the same irrational parts for them to be added or subtracted. What I mean by this is this. For instance, if you have A root B and C root B, if you look at this very well, they have the same irrational parts, the same sword parts. That's root B. Actually, they both have that, which is the same. So these two swords can be added or subtracted. But if you have, for instance, A root B and A root C, they do not have the same irrational part, so they cannot be added or subtracted. That's what I mean by the same basic form. So those, the last example cannot be added and subtracted. So for instance, if you look at 7 root 3, for instance, and 6 root 3, they both have the same basic form, which is root 3, so they can be added as 7 plus 6 root 3, which is the same thing as 13 root 3. But just like in the second case, 3 root 6 plus 3 root 7 cannot be added directly. So that just illustrates what basic forms mean. we'll just go to some examples at this time. I'll just want to test your knowledge of your understanding of what basic form means. So we have this question, 2 root 12 plus 3 root 48 minus 75. So the question here is, from this example, do you think all the parts have the same basic form? It's something you would really have to resolve, and I'll just give you some time to do this, and we'll then solve it together to see if you got the answers right. Okay. So the first step you need to do at this time is to find the prime numbers of each of the numbers in the root. So we will go ahead to solve this. So you have 2 root 12. The prime numbers, the prime factors of 12, you can actually break 12 down into 2 times 2 times 3 plus 3 root of 2 times 2 times 2 times 2 times 3, and then minus 3 times 5 times 5. So from this, you will see that 2 times 2 can actually be resolved further. This can also be resolved further, and this can also be resolved further. So the ones I have actually put in the brackets can be simplified further and brought outside the square root. So we will then bring these ones outside the square root at this particular point in time, since we know their root. So we'll have 2 times 2 root 3 plus 3 times 2 times 2 root 3 minus, so we have 5 root 3. So we can also just multiply this out, and this gives 4 root 3 plus 12 root 3 minus 5 root 3. So from this we can see they have the same basic form. So we have root 3 common to all of them. So from a question, you may not be able to directly tell if they have the same basic form without simplifying further. So from this now, you can further simplify this since they have the same basic form, and this would then become 4 plus 12 minus 5, all in bracket, root 3. So this gives 11 root 3. Let's look at another example here. I would also give you a bit of time to resolve this, and you would just need to follow the same steps we used in the first example. So yes, let's see if we got it right. The first thing would be to take 5 into the bracket. So we have 5 multiplying all you have in each of the brackets or in each of the square roots. So 5 will then have to go in. So you have 5 root 1.6 plus 5 root 0.4. You can still do a bit of expansion at this particular point to remove your decimal points. Removing the decimal points will really make life a bit easy. So all you need to do then is take 5 inside. Taking 5 inside would make it 5 times 5 times 1.6 plus root of 5 times 5 times 0.4. So multiplying this out gives root of 40 plus root of 10. So we can still do a bit of simplification at this point in time to see if they have the same basic form. if you look at the prime factors for 10, it's just 2 and 5, so we cannot reduce that further. And then for 40, we have 4 times 10 plus root of 10. The root of 4 is 2, so that means we have 2 root 10 plus root 10. So they have the same basic form. As such, they can be added. This gives 3 root 10. So let's take some further examples on multiplication of swords. You have to note at this particular point in time that for multiplication, they do not really compulsorily have to have the same basic form. So at this particular point in time, we then apply the multiplication rule and multiply out. So we multiply those outside the square root, which is 3 times 2. And then we multiply the ones inside the square root together. So this gives us 6 root 35.